what rheology is, right? Basically, it's understanding how fluids flow, right? And the basics of this is the fact that fluids flow, solids don't. So, what is the fundamental difference? If you apply a shear stress on a fluid, it tends to shear off, right? It cannot keep its shape. It will continue to deform. That is a fundamental definition of a fluid. And what comes under fluid then? What comes under fluid is any liquid, gas, everything is a fluid. And all of these materials cannot withstand shear. And what do you mean by saying they cannot withstand shear? If you apply a shear, these will continue to deform continuously. They won't come to rest. And that's where solid is different. I mean, unless you're looking at geological time scale, which Narayanan so eloquently put it. So basically, when you take a solid and you apply a shear, it will come to rest at some point. It will not deform beyond that, right? Assuming the stress is small. But no matter how small the stress, right? The way we understand fluid is that it will continue to flow. And that is where the differences start coming in. If you actually start peeping into that, that behavior under shear, is where we start seeing the different types of fluids. And Narayan has already introduced them. I will focus on the physical interpretations of this. What does it mean when we measure rheology? What is the physical behavior that I can expect when I say this is the rheological behavior I've obtained from, say, XYZ test, whatever that is? Now, before we do that, we need to understand why that's important, because if you look at printing process, and I think today morning Professor Surya introduced it to us, we are looking at an extrusion-based process. And Narayan already talked about extrusion-based rheology. That's coming your way tomorrow. That's a more heavy-hitting lecture there. So what do we do in this process, and what is of relevance to us? Material is pumped, which means it has to flow, right? So we need to understand how the material will flow when I pressurize it, right? So what is happening in this process? I mix concrete, dump it into a pump, which basically forces material to flow through a pipe. Essentially, it's flowing like a liquid, right? So I need to understand what is the flow under pressure. How does this material flow under pressure? We are used to doing this with water. We pump water. I mean, everywhere that you see, it's pumped. Then it gets extruded through a nozzle. It comes out through something. It comes through a pipe which is of much larger diameter. It goes through a nozzle which is much smaller. So it's almost like a squeeze flow that's happening there. So we need to understand what's happening here at the nozzle when it's being extruded, and what is the process happening there. Then it comes to rest. We put it, it comes to rest, right? So now you may say, well, is it still a fluid, or is it suddenly become a solid? Right? So what is it, that property of the fluid then, when suppose if it is extruded and it suddenly comes to rest and takes the shape of the filament, is it still a fluid or is it a solid? Because now it's at rest, and we associate that with solid behavior. But we need to understand that that is also a type of a fluid behavior. Okay. And then it has to allow buildup of layers. So what is it? Is it still a fluid behavior? Can I somehow quantify it? And what does that mean in terms of my printing behavior? So going back to the basics, I think Narayan has already introduced a lot of these things. We know that fluids cannot take shear stress. It all started with simple definition of viscosity, right? So what do we mean by saying viscosity? Well, we associate it as a resistance to flow. Right? Typically, what do we say? More viscous a liquid, more difficult it is for me to force it through something, if it is a pipe, or just to pour it out of a bottle, if it's a more viscous liquid, right? How do we quantify it? Now, the minute we say flow, we have to use a dynamic parameter. We cannot use a static parameter. Shear strain doesn't make any sense. Shear strain is a static measure. Because I'm talking about something that's flowing, then I have to look at a dynamic behavior. So that becomes a shear strain rate. Right? So now if you look at this classic experiment that is usually present in all fluid mechanics textbooks, how do we present flow? I have a fluid which is between two surfaces. If I apply, let's say I move the top plate, what happens? Basically, I introduce a velocity gradient. A velocity gradient is developed, right? Now, to move it here takes some resistance. It's not going to just move unless I basically apply some force here. How much force do I apply? That depends on the property of the liquid. Which property? That depends on the viscosity of the liquid, right? So you're trying to shear the liquid. If you look at it, the liquid is getting sheared between these two surfaces, and we are trying to measure what is the resistance that the liquid is giving when I'm shearing it. Shearing it under a dynamic condition, right? So shear rate, okay? How do we measure that? Well, we measure the shear stress as a function of shear rate. Okay, so how do we measure shear rate? Well, I have to infer it. I cannot directly measure it. How do I infer it? Well, assuming that I get a linear velocity profile, I'll say I can calculate what is the shear rate that's happening here, right? That's how I calculate the shear rate. Okay, two fundamental things come out of here. One is I cannot directly measure strain. I have to infer it, right? What I can measure is the force here at this end here. What is the force I'm applying on this plate to move it? That I can measure. I can measure the velocity of this plate, right? So those are the two measured parameters, and that's what we saw when we looked at the operating principle of the rheometer. So even in idealized situation like what we have here, I can measure the force that I'm applying on the plate and the velocity with which this plate is moving. What I don't know is what is the stress that is developing here. I can only infer it. And I do not know what is the strain rate at which this is happening. Now, why do I say that? What if this velocity profile was not linear? Then everything changes, right? Under the assumption that I get a linear velocity profile, then I can say, well, this is my strain rate, okay? And this is the resistance I get, assuming that the stress is uniform or fitting some theory to it. I come up with this theory, which is basically, we say that we define a material called, or a fluid called a Newtonian fluid, where we say that the resistance is directly proportional to the strain rate. What does that mean physically? Suppose, and we know water is a Newtonian liquid. What does that mean physically? If you look at it, shear stress, this is the resistance, the dependent variable, this is the independent variable. So faster you move, more resistance you will get from the liquid, right? Now, if you were to enter water softly, slowly, basically you will sink to the bottom. Well, human body is lighter, but any object says sink to the bottom. You take a dive and you hit water, let's say at 50 meters per second, it'll hurt like hell. You might as well drop on a concrete slab. Why? Because when you are entering very fast, you're shearing the water at a very fast rate. So what happens then? The resistance shoots up, right? It's as simple as that, right? This linear behavior between the rate at which you're deforming the fluid and the resistance it's giving, this is called classical Newtonian behavior. And water is a classical Newtonian liquid. Okay. Another thing to note here, starts off at 0. So when the shear rate is 0, you get 0 stress, which means if I was to enter the water very, very slowly, resistance would be almost 0, right? If and a simple example to do, suppose you have static water in a bucket of water and you try to push your hand through it slowly, it'll go through and you'll not feel much resistance. But you try to slap the water, it'll hurt. If you don't trust me, do it. You'll know immediately that you're dealing with water, which is a Newtonian liquid. Okay, so that is the physical meaning of viscosity. Now, that rate constant is the rate constant between the shear stress, which is the resistance, as a function of rate at which you're shearing it, right? And if this is a constant, right, then you're dealing with a Newtonian liquid. That's the basis. Where have we encountered it? Well, we see this in pipe flows of classic. Most of us have probably seen this in our first or second year fluid mechanics. When we try to calculate pipe flows, we know that if I force water through a liquid, you'll get a no slip condition at the top and the bottom. There'll be no slip here, right? So the velocity at the on the boundary of the surface here will be 0. The velocity profile builds up and you get a velocity profile where you have the highest velocity in the middle. And what determines this is basically the viscosity of the liquid. You basically create a shear stress across the height of the pipe. We are all used to handling this, right? We've done this in our first year, second year BTech curricula. Now, when you try to force water through a pipe, initially there is some time that it takes for the flow to develop. Once the flow develops, we call it the Poiseuille flow, the pressure drops. becomes almost linear with distance, right? And this is what we expect in classical Newtonian liquids. So this is something we are used to seeing, classical Newtonian liquids. Again, just to emphasize again, classical Newtonian is something where resistance increases with rate. Faster you move, more resistance you'll get, right? And the relationship between the shear strain rate and shear stress is linear. It's a linear behavior, right? Now, going forward, if I was to move further with this, how do I measure this then? I need some way to determine this property. I have a shear a liquid. It's very nice that I have that classical representation. How do I create that in the lab? I can't put a plate and start moving it. The reason is the minute I put a plate, it's very nice here in the middle of the plate, but the minute I come close to the edge of the plate, the flow condition will be different, or the stress condition will be different. When is this set up? When this is infinite and this is infinite, there are no boundaries. How do I replicate that condition? It's very nice to draw these cartoons, but how do I replicate this condition in the field, in my lab, of an infinite condition, right? So one clever hack is to basically try to see if I can somehow induce this shear stress. And now we're talking about in something like a cement paste, measure the response. And when I'm talking measuring the response, I can only measure the force. Okay. And then I can measure the deformation. From there, I have to infer what is the stress in the material and what is the strain rate in the material. Try to relate those two. That is the condition that I have to create in the lab. Now, what I want to do is my arrows are shifted. I'm sorry about that. So, what we have with cement paste is we have cement grains which are sitting in a Newtonian fluid. Water is Newtonian, right? And we've just seen in the previous presentation that when it comes to cement paste, it behaves anything but like a Newtonian fluid. So what has changed? It's the presence of the particles. So clearly, whatever is the particulate matter, which is the cement in this case, that will influence how the cement paste responds to the applied shear, right? Now, the cause and effect we can explore. But more importantly, what we need to understand is how do I create that condition in the lab, this infinite condition? How do I create this ideal, so-called ideal flow condition in the lab of no boundary, and so that I can measure the resistance to the applied shear? One clever hack for this is this geometry. It's called the parallel plate geometry. Now, why does it simulate the infinite boundary? Because if you think about it, there's no boundary. You keep going around in circles. There is no boundary. So I can actually get over the boundary effect with this geometry, right? So this arrangement where I put two plates in parallel with a small gap in between them and try to rotate this plate relative to this plate. So I have one fixed plate and one rotating plate. When I rotate, what will happen? This plate will force the motion, right? The fluid here will be at rest because it is stuck to this plate. The fluid here will be at rest because it's stuck to this plate, and you create a velocity profile in between. Essentially, you're simulating that condition over there, right? So this is the closest that you get to simulating something that is an ideal condition. Okay, small catch. What do we have to do? So we've somehow managed to get over the problem of the boundary, created an infinite kind of an artificially infinite kind of a flow with this circular flow pattern that we're setting up here, but we still have to infer what is the stress and the strain in the fluid in there. That's what we have to infer. Now, that's where those calibration constants that were introduced to you come into play. So, what are we doing here to measure the rheological properties? And what can I measure in the process? I can shear the fluid by applying a torque, which is basically given as that F function. What is F? F is my applied torque. And what is the V? It is the rotation. I can measure these two. These are physical variables that I can measure, right? What I need from there is this shear stress, which develops across here, which means that at some level, I have to be able to model the liquid. Okay. Now, one way I can get around it is if the gap is very small, then I can assume that, well, look, it is essentially similar to what I get with two parallel plates. That's something, an idealization I can make over there. But one of the problems with this, yes, I've overcome the problem of this infinite geometry, by getting the material to flow in a circle. But I still have a problem that if you look at this particular geometry, what happens here is that the strain across here is going to vary. The strain at the spindle or the shaft here is going to be zero. Right at the axis of the shaft here, the strain is going to be zero. That is not even going to be rotating. It's not going to displace. As you move away from the shaft, what is going to happen? The strain rate will actually increase, right? So that is also going to influence the stress rate. So while this looks quite simple and you say, aha, I have actually conquered one problem, you've created another problem, and that is the strain rates and the shear stresses are not going to be constant. And that is basically, you can essentially visualize it here, right? So what do we do then? What we try and do there is we basically measure the torque and the rotation, and we assume some kind of a flow pattern across this radial direction, and then we basically come up with something that relates the applied torque to an average shear stress. So some kind of an averaging is done, because if I don't do that, the stress is not constant across as I walk across the radius. Okay. Similarly, I do the same thing for the strain, because even the strain rates will not be constant. So when we use such a geometry, the parallel plate geometry, what are we doing? We are shearing the liquid by essentially forcing rotation of the top plate. We're forcing this plate to rotate, right? That induces a circular flow of material. That induces shear. I've overcome the problem of the boundary, but now I've created a variable strain field and a variable stress field. So what we do then is that we basically try to relate what I've measured with some kind of an average shear, average strain. Okay. And those are the calibration constants that we have to develop for this particular geometry. If you do not do that, right, what you'll end up with is this. And when you're doing rheological measurements, it's perfectly all right to report torque and rotation. You can certainly report those. The only problem is that every time we do some measurement, right, we expect to see shear stress and strain rate, and that relates to viscosity. Okay, so some of the purists who actually do rheological measurements don't report shear stress and strain rate from something like a parallel plate. They'll simply report torque and rotation values. Okay, so this calibration process basically accounts for the geometry that you're using. If you have a parallel plate, you get a different flow, and that has to be calibrated, because I need to relate the measured torque with the shear stress, and I need to relate the measured rotation, which is shown by V, with the strain rate that is developing in the liquid. So that calibration process, usually the way we do it is there are mathematical, it's a mathematical exercise. You can do this. You can actually develop these relationships. In addition to this, there's also one more factor, and that is if I was to spin the top plate, right, I'm measuring the torque, right? Where is the resistance to that coming from? Well, you'll say, well, the resistance is coming from this liquid that is on the bottom. That, as it is shearing, and that viscosity of that liquid is what is giving the resistance to the rotation of the top plate, right? Is that the only resistance? Whenever you rotate something, right, where does the resistance come from? Torque. In this case, it's clearly coming from the liquid that is here in the gap, right? It's getting sheared and it's giving you the resistance. Is there any other contributor that I need to worry about? Inertia. When you spin something, right, even if it were air, suppose I remove this liquid here and I simply put air, there'll be inertia. And that will also contribute to resistance. And that resistance also increases with the rate at which I spin this thing, right? That is the rotational inertia. So when I am trying to calibrate the measured torque with stress and measured rotation with the shear strain rate, I have to account for the inertial effect, right? And some kind of a geometry effect, which basically relates to the kind of, or the distribution of shear that is produced across the radius here. Both of these are built into those rotational constants into those calibration constants that we have. And these are usually programmed into the test machine. So whenever you use any tool, and I'll show you one more tool, which is perhaps better than this geometry. But even there, if you don't calibrate for inertia, you'll get erroneous results. Okay, you have to calibrate for inertia. You have to know the kind of the flow fields that you're setting up in the liquid when you try to shear it. Okay, now if this is such a problematic thing, this is perhaps a better geometry to measure. So what are we doing here? We have a cup, and then we have this concentric cylinder arrangement. What changes here? Basically, if you look at the liquid here, it's basically sheared between these two cylinders here. Again, I overcome the problem of this infinite geometry, because if you look at these two cylinders here, the material in the gap here is sheared essentially continuously, right? There are no jumps, there's no boundary. I've overcome that. And I essentially set up a nearly uniform flow field around here, unlike in the case of a plate. What happened in the case of a plate? When I was close to the axis, my flow was zero, or basically the strain rate was zero. As I moved away, the strain rate increases, right? Here that doesn't happen, because if the gap is small enough, the material is almost uniformly sheared in that small gap. Okay, but even here, I have to calibrate it. So once, if I decide to use this tool, the concentric cylinder, there's still the inertial effect, which I have to calibrate out. Otherwise, that will also contribute to the resistance. Because please remember, in the laboratory, I can only measure the torque. Okay, and I can only measure the rotation of the shaft. What I don't know is what's happening here in the liquid here. That has to be inferred, right? So the torque is basically the resistance that I'm getting. Where is the resistance coming from? In this case, it's the resistance from given by the liquid that is sitting in the small gap between these two cylinders, and inertia. So we try to basically, with our calibration constants, we try to calibrate out these two effects, the inertial effect and any variation in the stress field. And from there, we infer what is the shear stress and what is the strain rate that we get from any geometry that we use. So far we've seen two setups. One is a parallel plate, the other is a concentric cylinder. These are called geometries. So whenever you're doing rheological measurements, you have to be very clear about which geometry you've used to measure it. Okay, you cannot just report some value. You have to talk about which geometry was used. Okay, because the real experts in rheology would actually expect certain peculiar behaviors from certain geometries, and I'll show you that in a minute. Okay, and when you're doing your measurements, if you choose to just report the torque and the rotation, no problem. But if you're going to infer the fluid behavior, you better have a proper calibration done in your equipment. A calibration that takes care of the flow field and a calibration that takes care of the inertial effects. Now, what can I expect? Now, the other thing is, what kind of measurements do we make? In the laboratory, when we're talking about measurements, we call it a measurement protocol. We follow a certain protocol. What does protocol mean? How you want to shear the liquid. That's what a protocol is. And there are several protocols that are standard protocols that are followed. Okay. Now, suppose I choose the parallel plate geometry. I've chosen this geometry, which means that if I'm using this geometry in a rheometer, it's calibrated. Right? So what does that mean? It is calibrated would imply that whatever torque and the rotation I'm applying get converted into shear stress and strain rate, shear strain rate, and I get those two. Now the question is, what protocol do I apply? Now, the first protocol that I'd like to talk about is called the constant strain rate measurement. What does this mean? What we do is that we try to apply a constant strain rate on the material. We try to shear the material at a constant strain rate. Now, these are the kind of graphs that we typically report when it comes to protocol. What does a graph look like? So we'll say, okay, gamma dot as a function of time. Okay, so what did I say the protocol was? It's constant strain rate measurement. So that means the strain rate is constant with time. This is the protocol I applied. What kind of rotation profile would I get? If you look at the rotation, just by integrating it, you'd get a constantly increasing rotation of the shaft, right? So now, what am I doing in this? I'm shearing the liquid at a constant strain rate. What kind of response do I get from cement paste? Well, this is typically the response I would get. Please notice here, the y-axis is the stress. This is the stress I'm inferring. X-axis is the time. What happens when I increase time? The rotation that I'm applying to the liquid, that continues to increase at a constant strain rate. I'm basically shearing the material. The angle of shear in the liquid, this keeps on increasing with time. But if you look at the response, what do you get? Initially, in fact, for the cement paste, but for some very dilute cement paste, we'll get a nicely linear response. Okay, beyond which it will go to some peak, and after that the response crashes. Interpretation of there is a response leads us to this whole definition of yield stress. Now, what does this imply? If you look at the stress buildup being linear, which means that the material is almost behaving like a solid. When I try to shear it, I'm getting almost linear increase in shear as I'm increasing the total shear angle. It's behaving like a solid. That's what this linear part is. And this point at which it yields, beyond which is where the flow starts. So this basically becomes the point at which flow is initiated in the liquid, right? Now, why does this happen? So basically what I have here, yield stress, the way we define, is the effort that would be required to initiate flow in this liquid. It will not flow. Why? And the interesting thing is, suppose you were to load it up to this point and you were to unload it, it will unload back to zero, which means that it is behaving like an elastic solid. I've sheared it, I let go, it bounces back, right? So it's basically starting to behave like a solid, right? Now, there is a solid part of the response when I'm dealing with cement paste. And to induce flow, I have to basically go beyond a certain point, and only when I cross the yield stress does it start to flow here. So the initiation effort is what we call yield stress. This is very peculiar of cement paste and a lot of granular suspensions. So if I look at this, what we typically get, if you look at cement paste, I think Narayanan mentioned this, we have a typically concentrated suspension of solids, and you would get as what we call like a percolated network. So solid grains would all link up, and you'd get a skeleton that forms inside the paste. What is the skeleton made up of? It is cement grains that are making up the skeleton, and that skeleton is strong enough that initially when you try to shear it, it gives you a linear response. So if you apply a small shear, what would happen? The skeleton would deform. If you let go, it will bounce back, right? So that is what we get from the cement paste. Now, how do I then induce flow? I have to basically rupture that skeleton. I have to break that skeleton that's formed inside, right? And that is this point here. That is that stress that ruptures that skeleton, the internal structure that's formed inside the cement paste. And once I rupture the cement paste, then basically what happens, the resistance rapidly decreases. And at this point, it basically, these cement grains break up into floccules. They basically form flocks. And then here you see the shear stress essentially becomes constant after this point of time. That means now it is starting to behave like a Newtonian liquid. Okay, so what is happening here? Initially, there is some resistance to flow, which is coming from this skeleton that's formed inside. I shear it off, I break off the skeleton, then it starts to flow, right? And at that point, it kind of starts to flow like Newtonian, because here you look at it, the resistance, the shear stress with time becomes constant. And remember, I'm shearing the liquid at a constant strain rate. Okay. Sorry. Yeah. So how can we establish that there is a solid skeleton inside the cement paste? Suppose I do a simple experiment. It's called a step stress experiment. What's a step stress? Suppose I look at this response of the cement paste, and I say this is my yield stress. I can determine the value of this yield stress. Suppose I apply a stress in this range here and hold it constant. What do you expect to see? So if I apply this stress here, I basically shear off the liquid, it starts to flow. Suppose I apply a stress at this value and hold it constant. What do you think will happen? Remember, there's a skeleton of particles that's formed inside, right? The skeleton of particles is able to transmit some level of shear stress. And unless I smash that skeleton, unless I break that skeleton, it will not flow, right? So, and that value for smashing it is this value here. The initial part is almost linear, right? Suppose I apply this value of stress here, which is much lower than that stress that is required to break that skeleton. What would happen? You basically, exactly, the deformation should remain constant, right? That's exactly what we get when we do a step stress experiment. So this is a step stress experiment where the applied stress was half the yield stress. So you see, this is the kind of deformation that we measure as a function of time. It deforms and then it essentially stays constant. Okay, it's a different thing that if you continue here after a long time, it does creep, but that's a different issue. But basically, there is a skeleton which is formed with a network of cement particles inside the cement, right, which is able to transmit shear. Not a very large value of shear, but it is able to transmit shear. Okay, and for me to induce flow in this material, I have to break that skeleton. Okay, and that stress that's required to break that skeleton that formed inside the cement paste is yield stress. Yeah. So this is exactly what I expect to see. This, you see the skeleton here, and you get this percolated network of grains, which is able to transmit the shear stress across the skeleton. Now comes the other property of yield stress. What is this yield stress? And we said, well, yield stress is something that is required to induce flow, right? How do we measure yield stress? Typically, the way we measure it is using this slump cone. And if material has a yield stress, it is not going to be self-leveling. What do I mean by that? Suppose if I fill this cone with water and I lift the cone, what is going to happen? It'll essentially level out, right? It's not going to keep a shape like this. It's impossible for water to keep this shape. Why? What is the fundamental difference between water and cement in this case? Yield stress. Okay, water does not have a yield stress, and I'll show that a little later. But basically, when you look at this at a slump cone that has come to rest, it's a static condition. It's not flowing. It's come to rest, right? And basically, if I was to look at any plane passing through the cement paste here, and I can look at the stresses, I can calculate the stresses on that plane, there will definitely be shear stress present there, right? If I was to draw a plane going through this material here, right, I can do a stress analysis and I can figure out what are the stresses there. I will have some shear stresses, right? So what keeps that material from sustaining that shear? It is a yield stress. It's because cement paste has a yield stress, it is actually able to give you a finite slump value. And you can develop, there are several theories, I won't get into details of this, but basically you can actually relate the slump value with the yield stress of the material. And these are based on pure mechanics, where you can show that if the yield stress is zero, there is no way that it will keep this height. There's no way that it'll have a finite slump. Okay, if yield stress is set to zero in any of these mathematical formulations, you'll find that the only equilibrium configuration would be when this touches this. Okay, you cannot have any level differences. Okay, the only way you can create artificial level differences in water is if you have some support. You can put it in a container and have it keep the level differences, but by itself, water is not going to entertain level differences, right, in a self-supporting manner. So all these theories essentially would point you in the same direction. I'll skip this quickly. But now, remember, coming back to the measurement protocols, there's another measurement protocol that we typically do, which is basically the measurement of viscosity. How would I measure viscosity? Basically, I want to shear the material at a constant strain rate. So what we do in here is to ramp up the strain rate. We basically start from a strain rate of 0, keep ramping up the strain, and we measure the resistance to the fluid. This is another measurement protocol. What we saw previously was a constant strain rate measurement. Here what I'm doing is actually ramping up the strain rate, the rate at which I'm applying the strain rate, right? So basically, it's like accelerating the strain rate. I start with a 0 strain rate and I keep increasing the strain rate. The rate at which I'm shearing, that is what I'm increasing. Now, if it were water, what would I expect? My shear stress versus strain rate would give me a straight line graph. What I get from cement is basically what we call the Bingham plastic idealization. What has changed? It is still a straight line, right? But it doesn't start at zero. Why? If you look at it, this strain rate zero is the initial resistance that I get, right? So where is this initial resistance coming from? So if you look at any value of strain rate here, that means the material is already flowing. How did I get to the flow state? Only after I shear off the internal skeleton. So this initial value, the initial resistance is what we call yield stress. This is another interpretation which you get from a different measurement, except because it is coming from a strain rate ramp, this yield stress that we measure, which is nothing but this intercept of this graph, is called the apparent yield stress. Okay. How did we measure the yield stress previously? We sheared the material, right? Measured the resistance. At some point, the measurement peaked and then it started to flow, right? So, but what are we doing here? We're basically applying a strain rate and measuring the resistance, right? So this initial value before the flow starts, this value here is my yield stress. But because it is coming from a different measurement, this is called, this initial resistance is still yield stress, right? But it is called the apparent yield stress. Okay. And this is from this measurement protocol where I am actually increasing the strain rate at a linear ramp, right? Now, what is the consequence of the yield stress? Suppose I give you a material with a yield stress. What would change in the profile? And this has consequence for pumping, right? Um, this is the velocity profile that you see in the black line here, right? This is the velocity profile in a pipe. Suppose I take a Newtonian liquid. Now, what is a Newtonian liquid? Linear relationship between shear stress and shear strain rate, right? And we know that our classical theories work beautifully. I can do pressure flow in pipes and all that. We can even predict this flow. Now, if you look at the strain rates across this, how do you think the strain rates are changing? Now, if you look at the shear strain, let's say, not even the strain rate. Suppose I look at the shear strain around here. If you look at this point here, right, strain rate is zero, isn't it? Now, where do you think you have the highest strain rate? Right here. That's where the shear stress is the highest. Where is the maximum pressure felt? Right at the edge. That's where the shear stress would be the highest. Right at the diameter of the pipe. Right. Now, why is this of consequence? Suppose I told you that the material has a finite yield stress. What would change? Now, wherever I have very low values of this strain rate, what will happen? It will basically not even shear enough, right? That it may remain like an elastic material. So what happens? You develop this plug kind of a flow. So what happens? You develop this kind of a profile here. And what's happening in the constant part? That entire part is moving with a constant velocity. So a plug develops. Okay. So if I gave you, let's say, a cement paste and I told you do an experiment where you force the cement paste through a pipe, what you would find very different in the case of a cement paste flowing through a pipe is that a plug would develop. What does a plug mean? The central part of the pipe, this part here, essentially would move undisturbed. It will just go as one solid mass being pushed through. The shearing is all limited to this part here, the boundaries. Okay. So in a manner of speaking, right, this actually perhaps helps with the conduction or pushing the material through the pipe, because I'm able to develop this plug here. And there are mathematical theories that allow us to predict it. Now, cement paste has one more complication. So if you look at this graph here, right, how did this change compared to the Bingham plastic fluid? So if you look at this here, shear stress versus shear rate, except in Bingham plastic, this was a straight line. What is happening here? It's basically nonlinear. Nonlinear in a way that if you physically interpret it, the slope of this starts to decrease as you go up. What does that mean? Basically, what that means is that viscosity, right? The local viscosity is decreasing. And we call such a material as shear thinning. And these are materials that if you agitate them, would tend to loosen up. And you know the common example of ketchup, right? Try to pour a ketchup out of a bottle, good luck. The best way to do it is to simply tap it, vibrate it, agitate it. The more you agitate it, it becomes more and more fluid and it starts to flow, right? That's exactly what we get in cement paste. It's a shear thinning. So it is a material that has a yield stress and is shear thinning. That means if I agitate the material, it will flow easier. And where do we use this property of cement paste? Vibration, right? When we try to consolidate, what are we trying to do? We just agitate the cement, and basically we're relying on this property of shear thinning to get this material to loosen up and to flow and fill all the gaps and everything else, right? Now, that's as far as the measurement goes. So when you actually try to describe this, what happens? My viscosity is now a function of gamma dot. It's not a constant, right? And it depends upon the shear rate that you apply. The faster you try to agitate it, the local viscosity decreases, right? It starts to thin out. Now, one little artifact that I wanted to introduce, and that has to do with this kind of a behavior. This you already have seen before, stress as a function of time. I'm applying a constant strain rate. This is what I would expect to see, except when you have cement paste which has water in it, oftentimes we start seeing slip happening. A water-rich film forms at the surface of the parallel plate and it starts to slip. And when it slips, you see this sawtooth kind of a response. It's an artifact, right? What is an artifact? Or experimentally, if I say something is an artifact, what does that mean? This is not real behavior. This is not the real behavior of the fluid. It's something that is happening because my measurement system is not able to keep with the behavior of the fluid. It's slipping, right? So how do I get around this? And the slipping is happening because I have a smooth surface on top. The way to get around that is to use this vane tool. So what do? We basically introduce this vane. It has these blades which you introduce into the fluid, and then you try to apply torque to it. Okay. The complication here is, suppose this is my outer cylinder, this is my vane, and if I try to torque it, the flow field that is set up here is very complex. It's not straightforward, but I can still calibrate it. Okay, not easy, but can be done. And that is typically the tool that we do, where we can still get a value of the shear stress, relate the measured torque to the shear stress that is developing in the fluid. Of course, all of these are based on certain idealization or the other of the flow field that is set up with this tool. And people have also done simulations of this. Now, one last measurement, which is what we call the stress sweep measurement. Now, this is another protocol. What do we do in here? We basically introduce any measurement system or put paste in any measurement system. In this case, we put it in this case, we put it with a vane, and we start applying torque at a certain frequency. We fix the frequency and we slowly agitate the system. Okay. Now, if this amplitude, let's say, is very, very small, the torque amplitude, and let's say this amplitude is much smaller than the yield stress, what would happen? Remember, there's a solid skeleton that's already present inside the paste. What is a solid skeleton? It's all these cement grains that are formed a skeleton, and they're giving you a solid-like response. So if I apply a very small agitation, what will happen? It'll basically give you a solid-like response, right? So, and what happens if I continue to increase the amplitude of that? At some point, the material will shear off, right? So that is what is called a stress sweep measurement. And what we measure from there, we can measure both the elastic, which is the solid response, and the viscoelastic part, which is the G double prime. So if you look at the elastic response, basically, you see it would initially give you a constant G prime. What does that mean? It gives you a constant shear modulus. So what am I measuring here when I do a small agitation? I'm going back and forth with a small amplitude. I'm measuring the shear modulus of the skeleton that is present inside. The shear resistance that I'm getting from the skeleton inside, that shear resistance is constant. If I increase the amplitude, at some point, it'll just shear off. And so this is another measure that we use for our yield stress, as was described before. And for such a measurement, in fact, the vane tool is probably the best tool to do to determine the yield stress. One last thing I'd like to touch upon quickly is this measure of thixotropy. So we've already looked at cement paste. We said it's a shear thinning. It has a yield stress. Yield stress is that resistance that I get at just as the flow is initiating. Why? Because look at this. The x-axis is the shear rate. This is the shear stress, right? This value here is when the shear rate is 0, right? Which means this is a point when the flow is not started. Yes, I move away from this point is where the flow has started. So this intercept we said was the yield stress. Once the flow starts, if I agitate it more and more, it starts thinning. So this is a classical shear thinning kind of a response. Okay. So how do I define a shear thinning liquid? It is a liquid that is thinning when I increase the shear rate. And this definition should be very clear to you. And people often confuse this with thixotropy. Now, what is then thixotropy? Thixotropy is something similar, except it is measured as a function of time. So what is shear thinning? Shear thinning is when I'm measuring it as a function of shear rate. Okay. So how do I measure the thixotropic behavior? Well, suppose I was to ramp up the shear rate up to this point, and suppose I kept the shear rate constant here. I just applied that shear rate continuously at this value. What we would see in cement paste is that it would start off at this value here, and it would slowly start falling as I continue to shear it at the same rate. So what is happening in thixotropic material, or the way we are defining it, is that the shear resistance decreases as a function of time at the same shear rate. Okay, whereas shear thinning is when the resistance or the slope, the viscosity, that decreases as a function of shear rate. Okay, thixotropy is with time at a given shear rate, right? Shear thinning is as a function of strain rate. Okay. Now, what causes this? One can get into the understanding of the material. We know that cement has the skeleton that's formed inside. That's what gives us this yield stress here. It has a shear thinning behavior because, again, these once I smash the structure, the material basically forms these, or inside, if you could look inside there, it forms these flocks. Basically, several particles stick together, they form these flocks. Now, what happens when I do this thixotropic measurement? What am I doing in thixotropy? I'm basically at a constant strain shear rate here, right? I'm holding the shear rate constant. So what happens to the resistance I measure? The resistance decreases at a constant rate. Okay. Why does the resistance decrease? Well, these flocks that you have, as I'm shearing it at a constant strain rate, these flocks start to break down into smaller flocks. And that is why you see the resistance breaking down, because when you keep shearing it at a constant strain rate, you have a certain flock size of flocks that's formed. Those flocks slowly start decreasing in size. They start breaking up, and you see the resistance breaking down. Okay. Now, so this fundamental difference between thixotropy and shear thinning should be clear. And let me see what other gyan I wanted to give. Yeah, so thixotropy basically also would entail what is the energy that would take for me to smash the structure inside the cement paste. Okay, now the converse of it can also be looked at. Why? Suppose I have a cement structure. Where is that going to come in handy? If let's say the material has some skeleton inside, it's able to give me some resistance because of the skeleton. Where is that handy? Well, I can count on it to keep its shape, right? It's behaving like an elastic material. As simple as that, isn't it? And we saw that yield stress relates to the slump. If I have higher yield stress, what will happen? The slump will be smaller. It'll keep its shape, right? So in the internal structure that I have in the cement paste, right, that relates to the shape keeping ability of the cement, right? So the converse of it, suppose I smash the structure, I shear it at a constant strain rate, I smash the structure, all these floccules break down into smaller flocks. Now the question is, can it still keep its shape? Possibly not. So what would I do? I would basically do this experiment where I would smash, so let me go back here. I would smash the structure here and then ramp it down to 0 strain rate. Okay. Now, if I gave you this liquid that is sitting here at a 0, once I've smashed it completely, how do you think this liquid will behave? I've taken the liquid, I've sheared it. I've sheared it in such a way that I've completely destroyed the internal structure. Now you think it'll still keep its shape. Now do you think I'll still get the same slump value? Possibly, possibly not. Okay. Now, why is this of importance to me? Well, look at what happens in printing. I pump the liquid. It is tremendously sheared, right? It comes out of the nozzle, more shear on it. Then it comes to rest. Now the question is it the same liquid that started, or is it the same liquid as was when I started pumping? It's a different liquid. It has been sheared. Now the question is, will it still have the same slump value? Possibly not, right? Now, why is that important? Suppose that liquid is able to regain its yield stress very quickly. Then I have some faith that if I can produce a liquid, right, that can be pumped, sheared off, it comes to rest and again regains its yield stress, so it'll keep its shape, right? So this property that we have where the material basically has some structure, the structure basically gets smashed when I shear it at a constant strain rate, and the ability to recover is what we call basically thixotropy, of use to us, I should say. The classical definition of thixotropy is simply this: the smashing of the structure, the breaking of the structure, right, at a constant strain rate. Now, so there are different measures of this. This is a nice cartoon representation of what I expect from thixotropy. This is what I expect from my cement paste that is fit for printing. It should start out as a cube, which means it will have very high resistance to flow. This is basically the high slump material I'm talking about. It doesn't want to flow. It has a yield stress. It is happy keeping its shape. Once I start pumping it, it should basically turn into a sphere. Why? Because then it will roll very nicely on this surface, right? Why is that happening in the case of cement paste? Because the shear thinning liquid, as I shear it, it's going to thin out. It's going to make it easier for me to pump it, right? Then the minute it comes on the other side, what do I want it? It should immediately become a cube again, right? So this change from here to here and from here to here is what we call thixotropy. Okay, and how we measure it, there are 100 different measures of thixotropy, right? And I'm not sure I have enough time to cover it, but hopefully through this class, we will keep repeating these terms again and again, but it's important that you understand the fundamentals. What is viscosity? What is a Newtonian liquid? What is a shear thinning liquid? And what is thixotropy? Okay, and what is yield stress? Okay, and oftentimes I've even had papers rejected because somebody who's very comfortable in solid mechanics told me obviously cement paste cannot have a yield stress. Yeah, go figure, right? So that happens. But it's just nomenclature, how we define our yield stress. The one thing I'd like to point out is basically what are we doing in rheology of cement paste? Well, we want to understand the cement paste response to applied shear. Okay, the issue is we cannot directly measure shear. So what do? We measure torque. We try to infer the flow. From there, we come up with this rheological response. This is a textbook that I'd highly recommend. It's by Mesga, where all these measurement protocols definitions are very clearly defined, right? Very concise textbook. If you ever want to buy a book on rheology, please do get hold of this textbook. One last thing I wanted to cap off with is this video that anyway you'll see in the demo. So this is a use of vane tool for measurement. So this is the cup, right? So this is the cup into which you put the paste, right? That is the paste. You mix, of course, the paste externally. The cup is introduced into the rheometer. So this is the rheometer. The cup itself is fixed. And that is the spindle onto which you attach your vane. This is a vane tool that is being attached. And when you attach the vane tool, the first thing, so this is the vane tool. The first thing you do is you calibrate it. And usually these are auto calibrated, most of these new systems. And then you go through what is called a pre-shearing protocol. You don't directly start doing measurements. Any measurement typically has a warm-up period. And this is one of the constant strain rate measurement. You see what happens, the stress builds up, reaches the maximum, then you see it starts to flow. The material starts to flow. That peak stress is what we call our yield stress, right? The initial part of it, well, it's a, so that is basically your elastic part of the response. Okay. So with that, I'll stop. Any questions? I know I've been kind of been on a roll. Didn't even bother to check if any questions. You'll see all of this in the demonstration anyway. Okay. And you'll see this repeatedly again and again. Now, one of the problems that we have with measurement in concrete is we cannot do a physical measurement. It's one thing to measure it using a rheometer on paste. Concrete rheometers are still kind of a work in progress. So how to infer flow behavior of concrete is the next level, where we have to infer the behavior of concrete. And slump becomes our best friend. Okay. So tomorrow, in fact, when we look at proportioning and all these things will come back to haunt us again. Right? Okay, so I think I'm keeping them from their coffee break, isn't it?